Voyager 1 left Earth in 1977, crossed the edge of the solar system, and is now drifting through interstellar space. But what happens next? In 1 million years, where will this tiny human-made machine actually be? And what will still remain of it in the dark between the stars? Tonight, this journey follows Voyager 1 far beyond the planets, beyond the sun's fading reach, and into its almost unimaginable future. If this kind of deep space story is fascinating, please like the video, subscribe to the channel, and come along for the voyage. Far beyond the planets, far beyond the last broad sway of sunlight on familiar worlds, Voyager 1 moves through the Milky Way. Around it lies no empty void in the simple sense. Space at this scale is thin beyond ordinary intuition, yet it is still a place with structure, motion, and history. The spacecraft travels inside a great spiral galaxy made of stars, dark matter, gas, dust, magnetic fields, and radiation. This galaxy spreads across roughly 100,000 light-years, with most of its bright stars gathered into a flat disk, and with older stars extending above and below that disk in a wider halo. Voyager 1 is so small against that setting that it does not alter it in any measurable way. It passes through it as a grain might pass through a continent-sized wind carried onward without changing the larger pattern. The Milky Way is not still. Its stars orbit the galactic center, each on its own path, bound by gravity across spans too large for ordinary experience. Giant clouds of gas drift and shear. Magnetic fields thread through the interstellar material. Ancient supernova remnants expand and fade. Radiation crosses open distances from stars long dead and stars still shining. The whole galaxy turns slowly, not as a rigid wheel, but as a system in which different regions circle at different rates. Near the Sun's region, one orbit around the galactic center takes on the order of 200 million years. 1 million years measured against that cycle is only a small passage, a brief segment of one turn. Voyager 1 belongs to that setting. Even though it is commonly imagined as flying away in a straight line into a black and silent beyond its motion, always remains part of this larger galactic circulation. The stellar population around the spacecraft is not spread evenly. The Milky Way contains hundreds of billions of stars, but the distances between them are enormous. Most of the galaxy is not crowded. Even within the disk where stars are more common, a typical star is separated from its nearest neighbours by several light-years. This means that Voyager 1, though it travels at remarkable speed by human standards, moves through a region where the nearest suns remain very far away. The night that surrounds it, if night can be imagined, there is not densely jewelled in the way skies appear from within an atmosphere. There is no bright dome. There is a sparse and deep arrangement of distant points embedded within diffuse galactic light, and an all-enclosing darkness that is not truly empty, but only very thinly filled. That darkness contains matter. The interstellar medium is the name given to the thin material between stars. It includes atoms, charged particles, small dust grains, and magnetic fields. In some places, this material gathers into cold molecular clouds, dense enough for new stars to form. In other places, it becomes hot and rarefied after shock waves from exploding stars pass through it. The Milky Way is therefore not simply a collection of separate stars floating in nothing. It is a connected environment, a broad internal weather of matter and energy. Voyager 1 moves within that weather, though the conditions around it are extraordinarily faint compared with anything on Earth. A human-made object that leaves the planets does not step out of nature, it only enters a subtler part of it. The galaxy also carries a long memory. Much of the material through which Voyager 1 travels has been processed many times. Hydrogen born in the early universe becomes part of stars. Inside stars, nuclear fusion builds heavier elements. When stars die, especially in great stellar explosions, some of that enriched matter is thrown back into the galaxy. New generations of stars then form from altered gas. Planets, rocks, metals, water, and the chemistry of life all arise from this repeated cosmic recycling. Voyager 1 itself is made from substances shaped by that history. Its metals are refined from material forged in ancient stars. Its record frame wires and instruments are local arrangements of galactic matter given temporary human purpose. In that sense, the spacecraft does not merely travel through the Milky Way. It is also one of its products returning outward in another form. Light behaves differently at this scale than it does in ordinary surroundings. On Earth, light defines surfaces, distances, and edges. In the Milky Way, beyond the planets, it crosses enormous emptiness without touching much at all. Starlight can travel for years, centuries or thousands of years before meeting dust or a detector. Some light near Voyager 1 comes from nearby stars within the Sun's general neighbourhood. Some has crossed much greater distances inside the galactic disk. Some diffuse glow comes from unresolved stars and scattered light mixed with dust lanes and gas. There are also forms of radiation invisible to human eyes, including radio waves, X-rays, gamma rays, and the steady rain of cosmic rays which are high-energy particles moving through the galaxy. Voyager 1 is immersed in this radiation environment constantly. It cannot see the Milky Way as a person would see it, but its instruments encounter the galaxy as streams, fields, and particles. Scale remains the most difficult truth of this setting. The spacecraft is only a few meters across. The solar system, even when stretched far beyond the outer planets, is tiny compared with the galaxy. The distance light travels in 1 year, called a light year, is nearly 10 trillion kilometers. The Milky Way spans about 100,000 of those light years. Against this measure, the outward drift of a single spacecraft is minute. It is real, measurable, and historically extraordinary. Yet in galactic terms it resembles the movement of a speck across an ocean whose shoreline cannot be seen. This does not make the journey meaningless. It makes it clear. Voyager 1 enters not a narrow corridor with a destination marked ahead, but a vast and indifferent environment that continues in every direction, on scales the human body never evolved to picture. Within the Milky Way, gravity supplies order without producing simplicity. Every star, cloud, cluster, and remnant contributes to the overall field. Dark matter not directly observed, as light adds much of the galaxy's mass and helps hold its larger structure together. Because of this combined gravity, nothing in the disk moves independently for long. Motion is always relation. Voyager 1, like every star and grain of dust near it, follows a path shaped by masses near and far. Yet the field is smooth enough at its location that no violent change is expected. The galaxy is dynamic but not chaotic in the everyday sense. It is a patient system. Things change over millions of years, but most do so gradually. This is the true outer setting for Voyager 1's future. It travels not into pure emptiness and not out beyond nature, but within one region of one ordinary spiral galaxy among many billions in the observable universe. Its path is set inside a medium already in motion, inside matter, already enriched by ancient stars, inside darkness, already crossed by light and particles. The spacecraft appears lonely, only when measured against human company. Measured against the Milky Way, it is one more small object moving through a broad and continuous galactic sea. The Sun moves through the Milky Way as one star among many. It does not stand at the centre of the galaxy, and it does not remain fixed while its planets circle around it. It follows a broad orbital path around the galactic centre, carried by the gravity of the galaxy's visible matter and its unseen dark matter. This motion is steady and immense. The Sun travels at roughly 220 kilometers per second around the galaxy, though the exact value depends on how the local galactic motion is measured. At that speed, even a single year carries the solar system across a very large distance. Yet the orbit is so vast that one full circuit still takes on the order of 230 million years. Against that timescale, the whole span of human civilization is barely detectable. Voyager 1 begins as part of that moving system. Before it becomes an interstellar traveller, it shares everything that already belongs to the Sun. It shares the Sun's motion around the galaxy. It shares the movement of the solar system through the local region of interstellar space. It shares the inherited momentum of Earth as Earth circles the Sun, and of the Sun as it circles the galaxy. This is one of the most important facts in understanding where Voyager 1 will be in 1 million years. The spacecraft is not launched from rest into a still background. It is released from a world that is already moving at great speed in several different ways at once. Seen from Earth, a launch appears dramatic and direct. A rocket rises upward, then outward, then away. Seen from the larger galactic setting, the picture is calmer and more continuous. Earth moves around the Sun. The Sun moves around the galactic center. The local stars move with their own slightly different speeds and directions. The Milky Way itself moves relative to other galaxies. Voyager 1 enters that layered motion and then keeps going within it. Its own added speed gained through launch and planetary gravity assists is significant for leaving the solar system, but it is small compared with the speed the Sun already has around the galaxy. This means that over 1 million years the path of Voyager 1 is best understood not as a separate escape from the Sun's galactic journey, but as a slight divergence from it. The Sun's galactic path is not a perfect circle. Like many stars in the Milky Way disk, it follows an orbit that can be described more accurately as a gentle long-term oscillation around an average route. It drifts a little inward and outward relative to the galactic center over vast timescales. It also moves slightly above and below the galactic plane, the thin central disk where most stars and gas are concentrated. These vertical motions happen slowly on timescales of tens of millions of years. Over 1 million years, the Sun continues only a modest fraction of these larger cycles. The motion is real, but the change is gradual. The solar system remains in the same broad galactic neighborhood, still part of the disk, still embedded in the same large stellar population. Voyager 1 remains tied to this overall motion even after leaving the planets far behind. This can seem counterintuitive because the spacecraft is often described as leaving the solar system forever. That statement is true in the sense that it will not return to orbit the Sun or visit the planets again. But leaving the solar system does not mean leaving behind the Sun's galactic path. The spacecraft continues to move through the Milky Way in nearly the same general orbital stream as the Sun. It is more like a particle drifting away from a ship that is already crossing an ocean than an object departing a dock on a motionless sea. The separation between Voyager 1 and the Sun grows steadily, yet both continue to sweep around the galaxy together. 1 million years is long enough for this shared movement to matter. In that time, the Sun travels a noticeable arc around the galactic center. It does not complete anything close to a full orbit, but it advances by more than 1/100th of one revolution. That may sound small, yet in physical distance it is enormous. Over 1 million years, the Sun carries the entire solar system across millions of billions of kilometers through the Milky Way. Voyager 1 accompanies this drift while also moving outward relative to the Sun. As a result, the spacecraft's future position cannot be pictured simply by drawing a straight line away from the present solar system into a fixed map. The map itself is moving because the sun is moving and because the nearby stars are moving as well. This shared motion shapes every estimate of Voyager 1's future location. When astronomers project where the spacecraft will be relative to nearby stars, they must account for the velocity of the sun, the spacecraft's own velocity relative to the sun, and the motions of the stars themselves. There is no absolute still frame in ordinary galactic astronomy that behaves like a universal grid painted onto space. Instead, there are chosen reference frames useful for calculation, each tied to some measured motion. In one frame, Voyager 1 appears to recede from the sun in a certain direction. In another, both sun and spacecraft trace paths around the galaxy together. Neither picture is false. Each reveals a different part of the same physical reality. This sun's motion also helps explain why nearby stars do not remain permanently nearby. The stellar neighborhood changes over time. Stars pass one another at distances that are very large but still meaningful on galactic scales. The pattern of nearest stars shifts across hundreds of thousands and millions of years, because every star follows its own orbit through the galactic potential, the broad gravitational structure of the Milky Way. Voyager 1 therefore travels through a neighborhood that slowly rearranges itself. The sun moves. Other stars move. The spacecraft, sharing most of the sun's motion but not all of it, gradually takes up a slightly different place in that changing flow. This larger view strips away the idea that Voyager 1 has a single destination already waiting ahead. The spacecraft has a future course but not a marked endpoint. It is not aimed at a harbour in the stars. Its motion is the result of initial conditions and gravity, not of navigation toward a chosen world. The sun's galactic path is part of those initial conditions. Without the sun's existing motion, Voyager 1 would inhabit a different future entirely. The million-year story begins not with the spacecraft alone but with the star system that launches it, while already crossing the galaxy. So the sun is not merely the place Voyager 1 leaves behind. It is the moving source of the journey. It carries the planets, the distant cloud of icy bodies, the outer reach of the solar wind, and the departing spacecraft together around the Milky Way. Voyager 1 slowly peels away from that family of bodies, but it never stops sharing the larger drift. In 1 million years, the separation between sun and spacecraft becomes vast by human standards, yet both still belong to the same circling region of the galactic disk, both still take part in the same patient turning of one ordinary star around the centre of the Milky Way. The sun reaches far beyond the bright circle of the planets. Its visible surface is only the beginning of its outward influence. Light streams away from it in all directions, thinning with distance but never truly ending. Gravity extends outward as well, binding planets, comets, and smaller bodies into orbit across a region much larger than the familiar inner system. There's also a third reach less obvious than light and less intuitively felt than gravity. This is the solar wind, the continuous flow of charged particles escaping from the sun's hot outer atmosphere. Voyager 1 has passed beyond the planets and beyond the strongest familiar expression of these forces, yet the fading reach of the sun still defines the broad setting through which it has only recently moved. Sunlight is the easiest part of this reach to imagine. It travels at a constant speed through space, crossing the distance from the sun to Earth in a little more than 8 minutes. At the distance of the giant planets, it is much weaker than at Earth, and farther out it continues to fade according to a simple geometric rule. The same quantity of light spreads over a larger and larger area as it moves outward, so each square meter receives less of it. By the time sunlight reaches the far outer regions of the solar system, it is dim-cold in its effect and unable to warm objects in any familiar earthly way. Yet it is still there. A reflective surface, if turned properly, still catches it. A detector still measures it. Voyager 1 continues to be illuminated by the sun, though only faintly, even as the spacecraft moves through regions where starlight and interstellar conditions begin to matter more. Gravity behaves differently. Unlike sunlight, it does not weaken because particles spread outward. It weakens with distance through the structure of the gravitational field itself, but it never cuts off at an edge. The sun's gravity holds the planets in orbit and governs the paths of comets and distant icy bodies far beyond Neptune. Even where its pull becomes very weak, it still remains the dominant local force over a large volume of space. A body leaving the solar system never suddenly stops feeling the sun. Instead, the sun's pull gradually becomes less important, compared with the combined gravity of the galaxy and the passing influence of other stars. Voyager 1 is still under the sun's gravity now, and it will remain so for a very long time, even while no longer bound in an orbit that brings it back. This fading but persistent gravity is part of what makes the far outer solar system so difficult to imagine. The inner planets lie in a region where sunlight is still strong, and orbital times are measured in years. Beyond them, the giant planets occupy wider and darker paths. Beyond those worlds lies the Kuiper Belt, a broad population of icy bodies. Farther still, in the accepted picture of the solar system, there is the distant Oort cloud, not directly observed as a complete structure, but strongly inferred from the behavior of long-period comets. This cloud is thought to extend perhaps halfway to the nearest stars, a vast and sparse sphere of icy remnants, weakly held by the sun's gravity. Voyager 1 is not moving toward the dense heart of some outer wall. It is passing through a domain where the sun's control gradually loosens across immense and empty-looking distances. The solar wind gives the sun another kind of reach. It is made of charged particles, mainly protons and electrons, flowing outward from the sun's corona, the extremely hot outer atmosphere visible during a total solar eclipse. This flow is not uniform. It changes with solar activity, magnetic structure, and time. It carries the sun's magnetic field outward, stretching it into a spiral shape as the sun rotates. Near Earth, this wind helps shape space weather, influencing magnetic storms and auroras when it interacts with the magnetic field of a planet. Much farther away, long beyond the orbits of the planets, it continues to expand until it begins to lose its struggle against the pressure of the interstellar medium. The region filled and dominated by this outward flow is called the heliosphere, the sun's great bubble in space. Voyager 1 has already crossed the boundary where the solar wind can no longer push outward as a supersonic flow. Before that crossing, for most of its flight, it moves through a realm still ruled by the solar wind. This realm is not empty and still. It is a shifting extension of the sun's atmosphere and magnetic influence stretched across billions of kilometers. The farther from the sun, the thinner and weaker this flow becomes. Its particles are more dispersed. Its field is less forceful. Disturbances moving through it spread and fade. Yet for decades of travel, Voyager 1 remains within this solar domain even after all planets are left behind. The fading reach of the sun is therefore not only a matter of dim light and weakening gravity. It is also a moving physical outflow of plasma, a gas so hot that its atoms are broken into charged particles. At great distances, the relative importance of these three reaches begins to separate clearly. Light continues onward without caring much about the surrounding matter. Gravity continues as a weakening bond still acting, but no longer enclosing the spacecraft in a practical sense. The solar wind, however, must face the environment outside the sun's influence. It presses outward until the surrounding interstellar medium pushes back hard enough to slow and finally contain it. This makes the outer solar system unlike the inner one not only in distance but in kind. The planets orbit inside a system where the Sun easily dominates almost every major process. Voyager 1 moves into a region where that dominance becomes partial contested and then slowly surrendered. Even here, the Sun remains the main source of order in another sense. The direction away from the Sun still matters. The spacecraft's path is measured from it. Its speed is often given relative to it. Its electric power, though now extremely limited, comes from material prepared for a mission launched within its light. The very meaning of outwardness in Voyager 1's journey depends on the Sun as the centre of departure. Without that reference, the path is only one motion among many in the galaxy. With it, the spacecraft can still be described as moving deeper into the outer reach of the star that made the mission possible. So this region is not yet the true realm between stars. It is the far diminishing frontier of one star's influence. Light has faded but not vanished. Gravity has weakened but not ceased. The solar wind has spread until it approaches the limit of its outward authority. Voyager 1 moves through this thinning dominion as a tiny metal witness to how far a star can still matter when its warmth is faint, its pull is loose, and its surrounding wind is nearing its end. The heliosphere is the Sun's outer envelope, though it is not made of solid matter liquid or ordinary air. It is a vast bubble of plasma and magnetic influence formed by the solar wind, as that wind expands away from the Sun in all directions. Plasma is a state of matter in which atoms are broken apart into charged particles, mainly free electrons and atomic nuclei. Because these particles carry electric charge, they respond strongly to magnetic fields. The solar wind, therefore, does not simply spread outward as a neutral breeze. It carries the Sun's magnetic field with it, draping that field through space, and shaping a broad domain in which solar material remains dynamically important. Voyager 1 spends most of its long journey inside this envelope before finally crossing beyond it. This bubble is not perfectly round. The Sun moves through the local interstellar medium, and the surrounding matter presses back against the solar wind. As a result, the heliosphere is thought to be compressed somewhat on the side, facing the Sun's direction of motion, and stretched on the opposite side. Its exact shape is still an active area of research because the region is difficult to observe directly and must be inferred from spacecraft data, energetic neutral atom maps and models of plasma behavior. Observations indicate that the heliosphere has a definite outer boundary structure, but it remains uncertain in detail how smooth, blunt or tail-like that structure is at its farthest extent. What is clear is that the heliosphere is not an abstract line on a chart. It is a real interaction zone between the solar wind and the matter between stars. Far from the Sun, the solar wind changes character. Close to the Sun, it races outward faster than waves. In the plasma can travel back through it. In that condition, it is called supersonic, though the word refers here to plasma waves rather than sound in ordinary air. Eventually, the outward flow meets enough resistance from the interstellar medium that it must slow down. This slowing does not happen gently at first. It occurs across a boundary called the termination shock. A shock is a place where properties such as speed, density, and temperature change abruptly. When Voyager 1 crosses the termination shock in the year 2004, it enters a region where the solar wind has been slowed, heated, and made more turbulent. Beyond that shock lies the heliosheath. This is the outer layer of the heliosphere, a broad and disturbed region in which the weakened solar wind continues to push outward, but no longer in its earlier fast state. The plasma there is hotter and more compressed. Magnetic fields are distorted. Energetic particles behave differently from the way they do deeper inside the solar system. The heliosheath is not a place that can be seen as a glowing shell. It is known through measurements of particles' magnetic fields and plasma conditions. For Voyager 1, it becomes the final great zone of solar influence before the spacecraft reaches the boundary with true interstellar space. The outer boundary itself is called the heliopause. This is the surface where the outward pressure of the solar wind is balanced by the inward pressure of the interstellar medium. It is not a wall in the ordinary sense. No solid barrier stands there. Instead, it is a transition between two different cosmic environments. On one side lies plasma that originates from the Sun and remains part of the heliosphere. On the other side lies plasma that belongs to the interstellar medium outside the Sun's protective bubble. Magnetic fields continue across the region in complicated ways, and particles can cross or be excluded depending on their energies and the conditions at the boundary. Yet in physical meaning, the heliopause marks the end of the Sun's plasma domain. Voyager 1 crosses this boundary in the year 2012. The transition is identified not by a dramatic visual change, but by the behavior of particles and fields. One of the clearest signs is the sharp drop in lower energy charged particles associated with the heliosphere, and the corresponding rise in higher energy galactic cosmic rays entering from interstellar space. Later analysis of plasma wave data supports the conclusion that the spacecraft is moving through a denser medium than the heliosheath as expected outside the heliopause. The crossing is historically important because it marks the first time a human-made object is observed to enter interstellar space. Yet even here the reality remains subtle. Voyager 1 does not leave all solar influence behind in a single instant. Sunlight still reaches it. The Sun's gravity still acts on it. What ends is the Sun's direct control through the solar wind as a surrounding plasma environment. The heliosphere matters because it is more than a boundary marker for distant spacecraft. It shields much of the solar system from a larger flux of galactic cosmic rays. These high-energy particles come from energetic processes in the galaxy, including supernova remnants, and perhaps other powerful accelerators. The heliosphere does not block them completely, but it modulates how many enter the inner solar system and with what energies. During periods of stronger solar activity, this modulation changes. In this way, the Sun's outer bubble influences radiation conditions far inside it. Voyager 1, by passing through the heliosheath and beyond the heliopause, helps reveal how this shielding works and where its limits lie. Even after the crossing, the heliosphere remains behind Voyager, one not as a finished chapter in a simple journey, but as a structure the spacecraft has only just exited on a galactic scale. The bubble itself continues to move with the Sun through the local interstellar medium. It expands, responds, and changes over time as the solar wind varies and as the surrounding interstellar conditions shift. It is therefore not a fixed shell left motionless in space. It is a living boundary of plasma physics carried along by the Sun and continually renewed by material streaming outward from the corona. To think of Voyager 1 beyond the heliosphere is to understand what has been left behind. The planets, comets, and icy bodies remain within the larger sphere of the Sun's gravitational reach, but the heliosphere is different. It is the region where the Sun actively blows a bubble into the galaxy. Once the spacecraft crosses the heliopause, it no longer travels inside that blown cavity. It enters the surrounding medium directly. The heliosphere becomes an envelope behind it, still attached to the Sun, still enclosing the inner solar system in a changing shield of plasma and magnetic field. So this region is the Sun's outermost atmospheric frontier in the broadest possible sense. It is not warm, not bright, and not visible as weather is visible on Earth, yet it behaves like an extended breathing boundary around a star. Voyager 1 spends decades approaching its end, then slips across without spectacle, leaving behind the last full enclosure made by the Sun itself. What remains ahead is no longer the outer layer of one star's domain, but the thinner and older material that lies between the stars. Beyond the heliopause, Voyager 1 moves through the interstellar medium. This phrase sounds abstract at first, but it names something real and physical. The interstellar medium is the matter and energy that occupy the space between stars inside a galaxy. It is not dense like air, and it is not empty like a perfect vacuum imagined in simple thought. It is an extremely thin mixture of gas dust, magnetic fields, and energetic particles spread across immense distances and shaped by the life cycles of stars. In this region, the spacecraft no longer travels inside the Sun's own plasma bubble. It moves directly through the wider galactic material that has surrounded the solar system all along. The gas in the interstellar medium is mostly hydrogen with helium, as the next most abundant component and much smaller amounts of heavier elements. Hydrogen is the simplest element made of a single proton, with one electron in its neutral form. Because hydrogen is so common in the universe, it dominates the mass of diffuse interstellar matter. Some of this gas is neutral, meaning its electrons remain attached to atomic nuclei. Some is ionized, meaning it exists as plasma, with electrons separated from nuclei. Which state dominates depends on local conditions such as temperature, radiation, and recent astrophysical events. In some places the gas is cold and comparatively dense. In others it is warm and very thin. In still others it is heated to great temperatures by shock waves from exploded stars. Around Voyager 1, the interstellar medium is thin enough that the spacecraft can travel vast distances without anything resembling ordinary collision. A human hand placed there would not feel a wind. A human eye would not see a mist. Yet detectors can measure the environment because even sparse matter leaves signatures in plasma waves, particle counts, and magnetic field behavior. This is one of the great lessons of deep space science. A region can appear empty to the senses and still possess measurable structure. Voyager 1 does not sail through nothing. It enters a medium so rarefied that its reality becomes visible only through patient instruments and careful interpretation. Dust is also present, though, in much smaller quantity than gas. Interstellar dust grains are tiny solid particles made from heavier elements, such as carbon, silicon, oxygen, magnesium, and iron, often bound into minerals, carbon-rich compounds or ices depending on the environment. These grains are important far beyond their small total mass. They absorb and scatter starlight, help cool gas clouds, and provide surfaces where simple chemistry can take place. Over larger galactic scales, they contribute to the dark lanes seen in some nebulae and across parts of the Milky Way. Near Voyager, one dust is too sparse to create any visible haze, yet it remains part of the medium. One more reminder that the space between stars contains material with its own subtle texture. Magnetic fields thread through this material continuously. They are weak by everyday standards, but in such thin surroundings they matter greatly. Charged particles respond to magnetic fields, spiral around them, and move differently depending on their energies. These fields influence how cosmic rays propagate, how shockwaves travel, and how clouds of gas evolve over time. Voyager 1 carries instruments able to sense aspects of this magnetic environment, and those measurements help scientists understand the transition from heliospheric space to interstellar space. The field outside the heliopause is not simply a stronger version of the solar magnetic field. It belongs to the local interstellar medium itself, though the boundary region between the two can be complex. Energetic particles pass through this medium as well. Some are local in origin, others come from violent processes elsewhere in the galaxy. Cosmic rays, which are high-energy atomic nuclei and other particles, move through interstellar space and can travel enormous distances before interactions alter them. The heliosphere reduces part of their flow into the inner solar system, so one sign that Voyager 1 has entered interstellar space is the increased presence of galactic cosmic rays around it. This does not mean the region outside is suddenly crowded with particles in any ordinary sense. It means that the balance has changed. The sun's shielding bubble has fallen behind, and the broader galactic radiation environment becomes more directly apparent. Temperature in the interstellar medium is not simple to picture, because temperature describes the average energy of particles, not the total warmth an object would feel in the way it feels warmth in air. A gas can have a high temperature while remaining so thin that it transfers very little heat to a solid object. This matters in interstellar space. The local medium around Voyager 1 may be described in terms of thousands of degrees when considering particle energies, yet the number of particles is so low that the spacecraft is not bathed in heat as it would be inside a hot earthly gas. Its thermal state depends more on radiation balance and its own design than on any surrounding warmth in the ordinary sense. The interstellar medium is also a record of stellar history. Much of it has been shaped by earlier generations of stars that release matter through winds, pulses and explosions. When massive stars die as supernovae, they drive shock waves into surrounding gas, heating it, compressing it, and mixing in heavy elements forged in stellar interiors. Smaller stars enrich the medium more gently through long periods of mass loss. Over time, this material cools, drifts, mixes, and sometimes gathers again into clouds from which new stars form. The region through which Voyager 1 moves is therefore not merely between stars. It is part of the continuing cycle by which galaxies renew themselves. In this medium, boundaries are often broad rather than sharp. Conditions change from place to place. Density, ionization temperature, and magnetic structure vary across space. The local interstellar environment near the Sun is only one patch within the Milky Way's larger fabric. Voyager 1 samples that patch along a single narrow line. Its measurements are precious because they come from direct contact, yet they remain local measurements, not a complete map. From them, scientists infer the character of the surrounding medium, but uncertainty remains in the finer details of its variation over distance. So the interstellar medium is best understood as a thin and ancient ocean of matter and field, not visually dramatic, not empty and not uniform. Gas dominates its mass. Dust gives it grain. Magnetic fields give it structure. Energetic particles give it motion beyond simple drift. Voyager 1 now moves through this understated substance, no longer cushioned by the Sun's great bubble, but immersed in the wider material of the galaxy. Here the journey becomes quieter in one sense, and richer in another because the spacecraft has entered the actual matter between stars. The interstellar medium around the Sun is not one smooth expanse with the same properties in every direction. It is part of a more local structure, often called the local interstellar cloud, a patch of warm, partially ionized gas through which the solar system is moving. Partially ionized means that some atoms in the gas have lost electrons and become charged while others remain neutral. This matters because neutral atoms and charged particles behave differently. Neutral atoms can move across magnetic field lines without being guided by them, while charged particles are constrained by magnetic fields and plasma processes. Voyager 1 now travels within this nearby cloud sampling conditions in one narrow part of it, as the Sun and its heliosphere continue their slow passage through the same region. The local interstellar cloud is not large by galactic standards, yet it is immense by human standards. Its full shape is difficult to define sharply, because clouds in the interstellar medium often have fuzzy edges and internal variation. They're not like sharply bounded weather systems on Earth. Instead, they are regions where density, temperature, ionization, and motion differ enough from neighboring material to justify identifying them as distinct structures. The cloud around the Sun is understood through a combination of direct spacecraft measurements near the heliosphere and astronomical observations of nearby stars whose light carries absorption signatures from the matter lying between those stars and Earth. By studying these faint signatures, astronomers infer the composition speed and approximate geometry of the nearby interstellar gas. This local cloud is warm rather than cold in interstellar terms. Its temperature is thought to be on the order of several thousand degrees, though the thinness of the gas means that such a temperature does not produce warmth in the ordinary human sense. The density is low, with roughly a fraction of an atom to a few atoms per cubic centimetre, depending on what is counted and how ionization is separated. That is vastly thinner than any atmosphere humans experience naturally. Yet this small density is enough to matter when spread across trillions upon trillions of kilometres. It is enough to shape the heliosphere, to carry magnetic fields, to interact with cosmic rays, and to define the environment now surrounding Voyager 1. The local interstellar cloud is also in motion. The Sun and its heliosphere do not sit quietly inside it. They move through it, and the cloud itself has its own motion relative to nearby stars. This relative movement helps determine the shape of the heliosphere because the solar wind must push against an interstellar medium that is effectively flowing past the Sun. The front side of the heliosphere in the direction of this relative motion experiences stronger compression than it would in a perfectly still surrounding gas. Voyager 1 crosses the heliopause in a particular direction through this moving environment, meaning that its measurements reflect not only the general nature of the local cloud, but also the geometry of the Sun's passage through it. The cloud is not isolated in a simple sense. It appears to be part of a cluster or stream of nearby interstellar cloudlets, small adjacent regions of warm gas with similar but not identical motions and properties. The Sun may have entered the local interstellar cloud relatively recently on astronomical timescales, perhaps within the past tens of thousands of years, though estimates remain model-dependent. It may also leave it in the future and enter another nearby region with somewhat different density, ionization and magnetic conditions. This means the local interstellar setting is not permanent even for the solar system itself. It is a temporary galactic neighborhood. Voyager 1, however, remains inside the current local cloud for a significant part of its near future, since 1 million years is long enough for larger galactic changes, but also short enough that the spacecraft still samples the nearby interstellar environment, rather than crossing a major portion of the Milky Way. One of the most important features of this local cloud is its partial ionization. Neutral hydrogen and helium atoms from the cloud can penetrate into the heliosphere more deeply than charged particles can, because they are not directly deflected by magnetic fields. Some of these neutral atoms later become ionized inside the heliosphere through interactions with sunlight or charge exchange, a process in which an electron is transferred between a neutral atom and an ion. Once ionized, they can be picked up by the solar wind and accelerated. This creates a link between the local cloud and the internal particle population of the heliosphere. Even before Voyager 1 crossed the heliopause, the nearby cloud was already influencing conditions inside the Sun's bubble through this steady supply of neutral atoms. The magnetic field carried by the local interstellar cloud is another key property. Though weak in absolute terms, it has enough strength to affect the shape of the heliosphere and the transport of charged particles. Measurements by Voyager 1 after crossing the heliopause show that the magnetic field direction beyond the boundary does not differ as dramatically from the field inside as some early expectations suggested, which led to careful debate about how the crossing should be interpreted. Over time, however, the combined evidence from particle populations, plasma density and magnetic behavior strongly supports the conclusion that the spacecraft is indeed in interstellar space. This episode reveals something important about the local cloud itself. Its field is not merely background decoration. It is part of the active structure that shapes the boundary between the Sun's domain and the surrounding medium. Because the local interstellar cloud is warm, thin, partially ionized and magnetized, it represents a very specific kind of interstellar environment. It is not the cold, dense molecular gas from which stars are born. It is not the extremely hot, highly rarefied gas filling large cavities carved by ancient supernovae. It lies between these extremes, part of the modest and varied matter that can occupy the galactic disk between more dramatic regions. This moderation is important for Voyager 1's future. The spacecraft is not expected to encounter dense clouds, thick dust, or strong shocks within the timescale under discussion. Its surroundings are quiet by cosmic standards, though never perfectly uniform. Astronomers also place the local interstellar cloud within a broader surrounding feature often called the local bubble, a cavity of hot tenuous gas thought to have been shaped by past supernova activity. The exact relation between the cloud and this broader cavity remains an area of study, but the general picture is that the cloud is a denser warm structure embedded within, or near, a more rarefied local galactic region. This places Voyager 1 in a layered environment even now. It moves through one small warm cloud that itself belongs to a larger nearby galactic setting shaped by events that occurred long before the spacecraft was built. So this region is the nearest true interstellar neighborhood of the Sun, neither empty nor dramatic, but quietly specific. It has a measurable temperature, a measurable density, a measurable ionization state, and a measurable magnetic field. It presses against the heliosphere, leaks neutral atoms into it, modulates radiation conditions, and gives Voyager 1 its first enduring external environment beyond the Sun's bubble. The spacecraft now travels through this local cloud as a silent probe of the matter that has always surrounded the solar system, but only recently been touched directly by a human-made object. Voyager 1 moves at a speed that is extraordinary by the standards of human travel and still modest by the standards of the galaxy. Relative to the Sun, its speed is about 17 kilometers per second, a little more than 60,000 kilometers per hour. That pace is enough to cross continents on Earth in minutes, to move beyond the Moon in less than a day, and to pass the orbit of Neptune in a span that fits within a human lifetime. Yet in the space between stars, where distances are measured in trillions of kilometers, even this swift motion becomes quiet and patient. 1 million years is what gives the speed its true meaning. Only when ordinary velocity is allowed to persist for extraordinary time does the journey begin to take on an interstellar scale. Motion in empty-looking space has a simple character, when no strong force interrupts it. An object in motion continues in motion. This is one of the oldest and most reliable ideas in physics. Voyager 1 does not need to keep its engines firing in order to go on. Its main propulsion ended long ago. The spacecraft continues because once it was accelerated away from Earth, and then redirected and sped up by the gravity of giant planets, especially Jupiter and Saturn, there was no substantial drag to stop it. In interplanetary and interstellar space there is matter, but it is so thin that it cannot slow the spacecraft in any noticeable way over timescales of decades or even much longer. The future distance Voyager 1 will cover is therefore mainly a matter of time multiplied by its present speed, with only very gentle corrections from gravity over vast spans. At about 17 kilometers per second, Voyager 1 covers more than 1.5 million kilometers each day. In 1 year, it travels more than 500 million kilometers relative to the Sun. These numbers are already large enough to become hard to picture, yet they remain only the beginning. In 1,000 years, the spacecraft covers more than 500 billion kilometers. In 100,000 years, it covers more than 50 trillion kilometers. In 1 million years, it reaches a distance of roughly 17 light-years from the Sun. If its speed relative to the Sun remains close to its present value, and no major gravitational encounter alters it significantly. A light-year is the distance light travels in 1 year nearly 10 trillion kilometers. This comparison shows both the achievement and the restraint of the motion. After 1 million years of uninterrupted travel, Voyager 1 is still not crossing a large fraction of the Milky Way. It is only entering the scale of distances between the nearer stars. This kind of steady motion changes the meaning of time itself. For a person, 1 second is a moment. For a spacecraft crossing the outer solar system, 1 second is nearly 20 kilometers. 1 year is a major stretch of the mission. For the interstellar future of Voyager, 1 year is a small accounting interval. 1,000 years is a measurable but still local drift, and 1 million years becomes the first span large enough to answer the question in the title with substance. The spacecraft does not leap into the distant future. It accumulates it 1 second at a time, each second adding another short segment to a line that gradually becomes astronomical in length. There is also an important difference between speed and destination. Speed tells how fast the spacecraft moves. It does not by itself specify where it will be relative to everything else. The Sun is moving through the galaxy. Nearby stars are moving as well. The local interstellar cloud is not fixed like a backdrop painted around the spacecraft. So when Voyager 1 is said to be traveling at about 17 kilometers per second, that value belongs to a chosen frame of reference, usually relative to the Sun. This is the most useful frame for understanding how far it gets from its source. It is not the only possible frame, but it is the clearest one for describing the spacecraft's million-year separation from the solar system. Even in that sun-centered view, the magnitude of the journey becomes clearer when compared with familiar scales. Neptune orbits at about 30 times Earth's average distance from the Sun. The nearest star system, Proxima Centauri, and its companions in the Alpha Centauri system lies more than 4 light-years away. Voyager 1 is already far beyond the outer planets, but 1 million years of travel would carry it several times farther than the distance to the nearest star. Not in the direction of that star system, and not toward a planned arrival, but in sheer scale of separation. This is why long-duration motion matters so much. A speed that seems insufficient when compared with light becomes meaningful when compared with the patient architecture of the local stellar neighborhood. The constancy of the motion also reveals something about interstellar travel more broadly. Human imagination often prefers rapid movement, dramatic acceleration, and decisive arrival. Voyager 1 represents another model. It demonstrates that even modest speeds can penetrate the space between stars if enough time is allowed. The cost is not energy alone, but duration. The spacecraft has no practical way to brake steer actively across huge distances or preserve its instruments indefinitely. Yet as a physical object it still advances. 1 million years does not make it fast. It makes it far. This distinction is essential. The future position of Voyager 1 is not the result of some new burst of power. It is the accumulated outcome of a motion already established. There is a temptation to think that the vastness of the galaxy makes all such movement negligible. In one sense, that is true. The Milky Way is so large that 17 light-years is only a tiny local displacement. But another truth stands beside it. For a manufactured object built on Earth, launched in the 20th century, and measured against the scale of human history, a journey of roughly 17 light-years is immense. It moves the spacecraft well beyond the Sun's immediate stellar neighborhood and deep into a future no civilization can forecast in detail. Speed joined to time transforms a finite machine into a long-lived trajectory. So this region of the story is not defined by what surrounds Voyager 1 but by what its steady motion can accomplish. The spacecraft does not rush, it does not pause, it simply continues carrying forward the momentum given to it during a brief active mission. 17 kilometers each second becomes hundreds of millions of kilometers each year. Hundreds of millions of kilometers each year become trillions across long spans. Trillions become light years, and light years, when counted patiently enough, become the first true measure of where Voyager 1 can be after 1 million years of unbroken travel away from the Sun. Voyager 1 does not travel toward the future on a straight line drawn across a fixed map. Its path can be described as straight only in a limited and local sense. Relative to the Sun and over spans short compared with galactic cycles, the spacecraft continues outward along a well-defined course. But the Sun is moving, the nearby stars are moving, and the galaxy itself provides the broader gravitational setting through which all of these motions unfold. Because of this, the future track of Voyager 1 is best understood as a trajectory, not as a simple arrow. A trajectory is a path shaped by initial speed, direction, and gravity. It is not chosen moment by moment by active steering. It is inherited, sustained, and then modified only gently over long intervals. The present direction of Voyager 1 is known in relation to the plane of the planets and to the sky as seen from Earth. NASA describes the spacecraft as moving out of the plane of the planets to the north, roughly 35 degrees above the ecliptic, and in the general direction of the solar apex, the direction of the Sun's motion relative to nearby stars. It is also described as leaving the solar system toward the constellation Ophiuchus. These reference points are useful because they turn a remote motion into a picture that can be located in familiar celestial coordinates, yet they must be handled carefully. A constellation is a pattern as seen from Earth, not a physical target in space. The stars that define Ophiuchus lie at many different distances and do not mark a single destination. The phrase gives direction, not arrival. The shape of the path begins with the way Voyager 1 leaves the planetary system. It is not launched directly from Earth into interstellar space. First it escapes Earth, then it falls and climbs within the Sun's gravitational field, and then it gains additional speed and changes direction through gravity assists from giant planets. A gravity assist is a maneuver in which a spacecraft passes a moving planet and exchanges energy and momentum with the planet's orbital motion. Jupiter first accelerates and redirects Voyager 1. Saturn then changes the path again, bending it upward out of the ecliptic plane and setting the spacecraft onto the course it follows today. These encounters matter permanently. Once the planetary flybys end, the future track is largely the long consequence of the geometry established during those brief passages. This means the track has memory. The shape seen in the future is not random wandering. It carries within it the history of launch timing, planetary alignment, encounter distance, and the exact gravitational turning produced during the mission. The famous planetary alignment of the late 1970s makes the mission possible in the form it takes. Without that alignment, the trajectory would have been different or perhaps impossible within the same mission design. So when Voyager 1 is imagined 1 million years ahead, its position is not only the result of continued speed, it is also the preserved result of decisions and celestial opportunities present near the beginning. Relative to the Sun, the path is close to a line receding steadily outward. This is because once far from the planets, no strong nearby body remains to produce large bends. The Sun's gravity still acts, but its ability to curve the track decreases as distance grows. In the early outer mission, the path is more strongly shaped by the Sun because the spacecraft is still relatively near. Farther out as the distance increases and the speed remains sufficient for escape, the course settles into something that resembles a straight departure in sun-centered maps. This makes simple long-term estimates possible. It is why one can say that in 1 million years, Voyager 1 may be roughly 17 light-years from the Sun. But this line is only a line in that chosen frame. In the larger galactic frame, the track looks different. The Sun itself is moving around the Milky Way, and Voyager 1 carries most of that motion with it. So the spacecraft does not form a solitary ray, extending from a fixed solar system frozen in place. Instead, Sun and spacecraft both trace paths through the galaxy, with Voyager 1 slowly diverging from the Sun along the additional velocity gained during its departure. The separation grows, but the underlying galactic drift remains shared. The result is a path that can be pictured as a gentle branch opening away from the Sun's own route through the local stellar neighborhood. Nearby stars complicate the picture further. Each star has its own motion. This means that the future geometry of Voyager 1 relative to other suns changes continuously. A line drawn today toward some nearby star does not remain a line toward that same star over hundreds of thousands of years, because the star itself will have moved. For this reason, astronomers speak carefully when describing future close approaches. Voyager 1 is not aimed at a star that simply waits in place. It follows a course through a moving stellar field, and any future nearest approach depends on both motions together. The track must therefore be calculated as a relation among moving bodies, not as a shot fired toward a fixed target. The spacecraft also no longer steers itself in any meaningful navigational sense. Small attitude adjustments are used for communication and spacecraft management, while systems remain active, but these are not propulsive corrections that reshape the interstellar journey in a large way. The great arc is already set. This gives the future track a kind of stillness. It is not a path under continual guidance. It is a path released into persistence. Time carries it forward more than control does. Over 1 million years, this shape remains mostly smooth. Gravitational disturbances from passing stars are possible in principle, but large changes are not expected unless an encounter is unusually close, and such close encounters are rare in the sparse stellar environment of the solar neighborhood. The path therefore remains to first order the one already established outward from the Sun north of the planetary plane, in the general direction of the solar apex through interstellar space and into the slowly changing arrangement of nearby stars. So the future track of Voyager 1 is shaped less like an adventurous search and more like a long quiet consequence. It begins in the moving Earth bends through the gravity of giant planets, rises out of the ecliptic, and then continues through a galaxy that never stands still. It points toward a region of sky, but not toward a chosen world. It grows farther from the Sun without leaving behind the Sun's larger galactic motion. Its shape is the preserved form of an old mission geometry extended across immense time. As Voyager 1 continues along its set course, the nearest stars do not stand still before it, like lamps placed in a dark hall. They move through the galaxy on their own paths, each carrying its own history of motion around the Milky Way. Because of this, the future of Voyager 1 among the stars is not a story of approaching one fixed destination. It is a story of passage through a shifting neighborhood. Over tens of thousands and hundreds of thousands of years, the spacecraft slowly changes its relation to nearby stars, while those stars change their relation to the Sun and to one another. The stellar neighborhood is sparse, but it is not static. The nearest known star system to the Sun at present is the Alpha Centauri system, including Proxima Centauri more than 4 light-years away. Other nearby stars lie at distances of several more light-years. These distances are small by galactic standards and enormous by human ones. At Voyager 1's speed, even the nearest of them would require tens of thousands of years to approach if the spacecraft were headed directly toward it. But it is not. Its path leads elsewhere. This fact is essential. Voyager 1 will pass through the local stellar region, but it is not bound for the nearest stars and will not make a close approach to them, simply because they are nearby to the Sun now. Astronomers have projected the spacecraft's future motion relative to surrounding stars. One commonly cited estimate is that in about 40,000 years, Voyager 1 will pass within roughly 1.5 light-years of the star Gliese 445, a faint red dwarf in the constellation Camelopardalis. This is a close pass in the loose language of stellar astronomy, but it's not close in any practical sense for travel or encounter. A light-year is such a large distance that 1.5 light-years still represents a gulf of nearly 15 trillion kilometers. No detailed visual meeting would occur. No planetary system, if one exists there, would fill the sky. The spacecraft and the star would merely come into a looser temporary nearness than most stars ever achieve with one another. This future pass illustrates the true scale of the local stellar neighborhood. Even when trajectories bring two objects into their nearest approach, over tens of thousands of years, the separation usually remains immense. Stars are small compared with the emptiness between them. Voyager 1 will not weave among them in a densely packed field. It will move through a region where the most notable encounters are still measured in light years. The nearby stars are neighbors only in a cosmic sense. They are not crowded landmarks. They are remote fires separated by darkness so broad that even a fast spacecraft spends millennia crossing fractions of it. The stars themselves vary greatly. Red dwarfs like Gliese 445 are smaller and dimmer than the Sun, and are by far the most common stars in the Milky Way. Some nearby stars are brighter and more massive. Some are white dwarfs, the dense remnants of once ordinary stars. Some belong to multiple star systems in which two or more stars orbit a shared center. Each has its own motion through the galaxy, usually measured in kilometers per second, and each changes place slowly but steadily over time. This means that the shape of the stellar neighborhood 1 million years from now will not match the one seen today. Some stars that are now among the Sun's nearest neighbors will have drifted farther away. Others now more distant will have come somewhat closer. Voyager 1 enters this rearranging neighborhood without any ability to respond to it. It does not choose among stars. It does not turn toward the more interesting ones or away from the less important ones. It simply continues on the line established long ago. The future stars it passes nearest to are determined by relative motion, not by mission design. This gives the journey a quiet impersonality. The spacecraft carries human memory and intention in its record and construction, but its million-year route among the stars is governed by mechanics alone. In that sense, the stellar neighborhood receives Voyager 1 not as a visitor with a schedule, but as a drifting object that happens to pass through. As the spacecraft leaves the Sun, farther behind, the Sun itself gradually becomes one star among others, from Voyager 1's perspective. At first, it remains a privileged reference point because all distances are measured from it. But over great spans, if the spacecraft could somehow observe its surroundings as a conscious witness, the Sun would become another moving light in the wider field, brighter than many stars at first, then less distinguished as distance increased. After 1 million years, when Voyager 1 may be roughly 17 light-years from the Sun would still be a relatively nearby star in astronomical terms, but no longer the overwhelmingly central object it is today. The spacecraft would then inhabit a region where several stars lie at comparable orders of distance. This shift in perspective matters because it changes the meaning of place. Close to Earth place is defined by planets, moons, and the Sun's immediate dominance. In the interstellar future, place is defined by proximity to stars measured in light years, by relative motion, and by the sparse geometry of stellar neighbours. Voyager 1's path becomes a thread laid through this loose, three-dimensional pattern. Its future is not the crossing of named borders, but the gradual alteration of which stars count as nearest and which as remote. The 1 million year timescale deepens this effect. In that span, Voyager 1 may move past several stars at broad distances without ever entering what would reasonably be called a stellar system in a close sense. It may leave the Sun's immediate neighbourhood and draw somewhat nearer to other stars, yet still remain in the same general sector of the galactic disk. This is enough to make the future track truly interstellar, but not enough to make it a voyage from one planetary system to another in the way human stories often imagine. So the passing of nearby stars is a calm and measured process. There are no dramatic flybys expected, no planned arrivals, and no dense clusters of suns crowding the route. Instead, there is a slowly changing arrangement of distant stars, each moving on its own path, with Voyager 1 slipping among them at a speed that only immense time can make significant. Its journey through the stellar neighbourhood is therefore not a sequence of encounters in the ordinary sense. It is a gradual redefinition of what counts as nearby in a region where even the nearest lights remain far apart. Gravity continues to act on Voyager 1 long after the spacecraft has left the planets behind. It does not act only at moments of dramatic encounter. It is always present, though often in forms so gentle that their effects become visible only across immense spans of time. This is the nature of the next region in the story. The spacecraft's future path is not expected to be transformed by sudden collisions or violent captures. Instead, it is shaped by small and patient gravitational influences that accumulate slowly. The Sun still pulls on Voyager 1. Nearby stars contribute faintly. The wider mass of the galaxy provides the broad field through which all motion proceeds. In 1 million years, these influences matter, not because they are large at any single moment, but because they never entirely stop. The Sun remains the most immediate gravitational source for a long time. Even after Voyager 1 crosses the heliopause and enters interstellar space, it does not leave the Sun's gravity behind. This can seem surprising because the phrase leaving the solar system often sounds absolute. Yet gravity has no sharp outer wall. The Sun's pull weakens with distance, but it continues outward indefinitely. What changes is not whether the Sun acts, but how strongly it acts compared with other influences. Close to the Sun, planets and spacecraft move in bound orbits. Farther away, a body can still feel the Sun's attraction, while possessing enough speed to avoid falling back. Voyager 1 is in that condition. It remains under solar gravity, but on an escape trajectory. An escape trajectory does not mean a perfectly straight line in the strict mathematical sense. The Sun's gravity continues to bend the path slightly, especially in the earlier outer stages of the journey. If the spacecraft had no solar gravity acting on it, after the planetary flybys its line outward would be simpler. But because the Sun continues to pull, the trajectory is better described as a hyperbolic path, a curve associated with an object that approaches a massive body, swings through its influence, and then departs with enough speed never to return. Far from the Sun, this curve becomes harder to distinguish from a straight line in practical maps, but the underlying gravitational story remains. Voyager 1 is not merely coasting in indifference. It is departing along a path continuously shaped, though ever more weakly, by the star it leaves behind. Other stars also exert gravity. Every star in the local neighbourhood contributes something to the overall gravitational environment, just as every mass in the galaxy contributes to the larger field. Yet at the great separations typical of interstellar space, the pull from any one nearby star is usually extremely small. Most stars lie too far away to produce more than a tiny perturbation on the path. A perturbation is a slight change in motion caused by an external influence. Over decades or centuries, such perturbations are too small to matter for Voyager 1's route. Over hundreds of thousands and millions of years they can become part of the total account, but even then they are expected to alter the path only modestly unless a star passes unusually near. This is why close stellar encounters matter more in principle than most of the surrounding stars do. If Voyager 1 were to pass very near a star, that star could bend its course more noticeably, perhaps changing its direction by a measurable amount or altering its speed relative to the Sun. But the stellar neighbourhood is sparse. Passes at distances of a light year or more are already considered relatively near in this context, and at such distances the gravitational effect remains gentle. The projected future approach to Gliese 445 at roughly 1.5 light years in about 40,000 years is important as a positional event, but it is not expected to produce a dramatic gravitational redirection. The star is simply too far away for that. A meaningful bending of the trajectory would require a much closer passage, and such passages are rare. The galaxy itself supplies the broadest gravitational field of all. The Sun, the nearby stars, the gas between them, and the unseen dark matter all contribute to the mass distribution of the Milky Way. This collective field guides the motion of stars around the galactic centre, and therefore also guides the motion of Voyager 1. Yet because the spacecraft and the Sun share most of their galactic movement, the galactic field does not quickly separate them in any dramatic way. Both continue along similar large-scale paths through the Milky Way. The spacecraft's divergence from the Sun is mostly the result of its additional speed, relative to the Sun laid on top of the motion they already share around the galaxy. The galactic field sets the stage, but within that stage the local separation remains a more delicate matter. This layered gravity gives the future path its character. Solar gravity dominates the local departure. Stellar gravity from nearby suns adds only faint adjustments, unless an uncommon close pass occurs. Galactic gravity supplies the continuous large background. None of these forces vanish, but their relative importance shifts with scale. Close to the Sun, the story is clearly solar. On larger spans, it becomes a mixture of solar departure and galactic drift. At no point in the next million years is Voyager 1 expected to become free from gravity altogether, because nothing in the universe is free from gravity altogether. What changes is the pattern of which masses matter most. There is also the question of drag from interstellar matter, but here gravity and material resistance differ sharply. The gas and dust around Voyager 1 are so thin that they do not slow it in a meaningful way over the period under discussion. A dust grain may strike the spacecraft now and then, and radiation may alter its materials, but the bulk motion through space remains essentially unaffected by drag. So when the future path bends, it bends because of gravity, not because interstellar space behaves like a fluid resisting passage. This makes the motion cleaner, quieter, and easier to project. The main uncertainties arise not from friction, but from the exact future geometry of gravitational encounters in a moving stellar field. 1 million years is long enough for these small deflections to have some cumulative effect, but not long enough to erase the basic identity of the trajectory. Voyager 1 still remains a craft departing the Sun on the path given to it by the mission design and the planetary flybys. Its line may curve slightly in relation to different frames. Its relation to nearby stars may shift as both sides move, yet the larger truth stays steady. No known force is expected to halt it, capture it, or turn it sharply aside in that interval. So this region of the story is one of patience rather than drama. Gravity continues everywhere, but mostly as a slow guidance rather than a sudden command. The sun keeps hold weakly while allowing escape. Passing stars whisper at the path more than they seize it. The galaxy carries both sun and spacecraft through its broad field without making either one the center. Voyager 1 therefore enters its million-year future under constant influence, yet with no strong hand likely to interrupt its long, quiet departure into interstellar space. Voyager 1 is already becoming quiet. The spacecraft still returns a limited stream of data, but this active phase belongs only to a small portion of its total future. Its electric power comes from radioisotope thermoelectric generators, devices that convert heat from the natural decay of plutonium into electricity. This power source does not fail all at once. It declines steadily over time as the radioactive material produces less heat, and as the systems that convert that heat into usable electrical energy age. Because of this, the spacecraft's working life is a long reduction rather than a sudden ending. Instruments are turned off one by one. Heating is managed carefully. Engineering choices are made to preserve communication for as long as possible. Yet the direction of the process is clear. Voyager 1 is moving towards silence. This silence must be understood precisely. A silent spacecraft is not the same thing as a stopped spacecraft. On Earth, machines often cease activity because friction atmosphere corrosion or loss of fuel prevents motion. In interstellar space, the situation is different. Voyager 1 can lose power, stop transmitting, and become completely inactive in every engineering sense, while still continuing through space at nearly the same speed. The spacecraft does not need electricity in order to keep moving. It needs electricity only to operate instruments, maintain some forms of control, and send signals home. Once those functions end, the body of the craft remains in motion, as surely as it did when it was alive with telemetry. The future of Voyager, one after the end of power, is therefore not the future of a dead object at rest. It is the future of a dead object still travelling. The decline in power is governed by physical law. Plutonium-238 decays at a predictable rate, with a half-life of a little more than 87 years. A half-life is the time required for half of a radioactive substance to decay. This does not mean the power supply is cut in half all at once at one moment. It means the available heat output decreases gradually and continuously. The mission was designed with this decline in mind. At launch, the power supply was high enough to support many instruments and systems. Decades later, that supply is far smaller, which is why mission teams continue to make careful trade-offs. The long interstellar future, however, extends far beyond any practical mission operations. Within a timescale of decades, then perhaps not too much more than that the spacecraft will no longer be able to sustain scientific observations and radio communication. Communication itself depends on delicate conditions. A functioning transmitter must have power. The spacecraft's antenna must remain oriented well enough toward Earth. Ground systems must also be capable of receiving the weak signal. Even while engineering teams preserve these conditions with remarkable skill, the signal is already extraordinarily faint because of the immense distance. As Voyager 1 moves farther from Earth, the challenge grows. But even if communication could somehow be sustained a little longer than expected by clever management, the deeper truth would not change. The spacecraft's active life is temporary. Its inertial life, the life of motion without function, is vastly longer. There is philosophical temptation to say that once Voyager 1 can no longer send data, the mission ends. In one practical sense, this is true. The scientific mission depends on received measurements. If no signal comes back, then no further observation is available to humanity. yet the object itself continues to exist and continues to move along the trajectory already established. The difference is between mission and motion. Mission belongs to human intention, operation, and knowledge. Motion belongs to physics. Mission can end while motion remains. This distinction becomes central in thinking about 1 million years. Almost all of that span lies after the end of Voyager 1 as an operating spacecraft. Nearly the whole million-year future belongs to Voyager 1 as an artifact in transit. The craft may retain some limited internal stability for a time after science operations cease. Its structure will still exist. Its spin state may persist with gradual change. Residual thermal patterns will continue until all short-term imbalances settle. But none of this means activity in the ordinary sense. There will be no new course correction of consequence, no fresh observation sent home, no continuing dialogue between Earth and the spacecraft. The long future is not one of ongoing exploration as humans usually imagine it. It is one of continued travel after exploration in the engineering sense has fallen silent. This makes Voyager one unusual among human creations. Most objects built by human beings are designed for brief use, compared with their material lifetime. A tool may last decades, but be used for only minutes at a time. A building may stand for centuries but remain in one place. Voyager 1 combines short operational life with immense spatial consequence. The period during which it actively functions is tiny, compared with the period during which it will remain a moving body in the galaxy. Its useful life as a probe is historically important but cosmically brief. Its existence as matter on a trajectory is likely to outlast not only the mission team and present institutions, but perhaps much of what now feels permanent in human history. There is also a calm lesson in this transition from power to silence. Human technology often appears meaningful because it acts, measures, computes, and responds. Voyager 1 shows another kind of persistence. Once its last instrument falls quiet, its importance does not vanish. It becomes a record of motion, a preserved outcome of a past civilization's technical ability and curiosity. It no longer studies the interstellar medium for Earth, but it still occupies the interstellar medium. It no longer reports its position, but it still has a position. It no longer maintains a mission, but it still carries one in the form of its construction and direction. So the end of power is not the end of the journey. It is the end of voice. The radioisotope generators fade, the instruments are silenced, the carrier signal disappears into the dark, Earth no longer hears from the craft. Yet Voyager 1 continues on, unchanged in the most essential physical fact of its future. It remains in motion. In 1 million years, what matters most is not when the last transmission ends, but that after the transmission ends there are still almost 1 million years left for the silent spacecraft to keep going. Voyager 1 is not only a trajectory, it is also a physical object made of particular materials arranged for a particular purpose. To understand where it will be in 1 million years, it is not enough to know how it moves. It is also necessary to understand what exactly is moving through interstellar space. The spacecraft is a compact assembly of metals, electronics, insulation, fuel residues, wiring, structural supports, instruments, and antenna surfaces, all designed in the 1970s for a mission expected to last years, but robust enough to persist far longer as matter. Long after its power fades, these materials remain. They do not continue as a machine in the full operational sense, yet they continue as an artifact, a constructed body of terrestrial origin travelling through the galaxy. The overall shape of Voyager 1 is distinctive. A large high-gain antenna shaped like a dish several meters across dominates its form. This antenna is made to send and receive radio signals across great distances. Behind and around it sits the main body of the spacecraft, containing electronics instruments and support systems. Extending outward are booms that carry scientific instruments, and the radioisotope thermoelectric generators away from the central body. These booms help reduce interference and manage heat and radiation. The arrangement is not elegant in a decorative sense. It is practical, asymmetrical, and mission-driven. Every exposed surface reflects engineering choices about communication power, thermal control, and measurement. Much of the spacecraft is built from aluminium and other durable metals. Aluminium is light, strong, and resistant to corrosion in ordinary terrestrial use, which makes it valuable in aerospace engineering. Voyager 1 also includes steels, copper-soldered joints, plated contacts, and specialized materials in electronics and structural components. The dish supports fasteners and equipment housings, all contribute to a body designed to survive launch vibrations, vacuum, thermal cycling, and decades of operation far from repair. The craft is not a solid block. It is a structured framework of joined parts, many with thin walls and carefully chosen tolerances. This means its long-term physical future depends not only on the durability of individual materials, but also on the endurance of the joints' coatings and interfaces between them. The electronics inside Voyager 1 belong to an earlier technological era. They are rugged, comparatively simple by modern standards, and built with reliability in mind. Circuit boards, transistors, connectors, memory components, and sensors occupy the protected interior. During the active mission, these parts interpret instrument signals, manage spacecraft functions, and shape radio communication. After power loss, they become inert material. Their physical presence remains, but the distinctions that once mattered operationally between processor, sensor, and communication chain no longer carry functional weight. In the million-year future, these components endure not as active systems, but as layered arrangements of metals, ceramics, semiconductors, and polymers slowly aging in a nearly empty environment. Insulation and coverings are also important. The spacecraft contains blankets and thermal control materials designed to retain or reject heat where needed. Some are made from polymer films coated with metals, forming multi-layer insulation that is highly effective in vacuum. Cables are wrapped in protective materials. Surfaces are painted plated or otherwise treated for optical and thermal reasons. These less visible parts may be among the more vulnerable over very long times because thin films, coatings, adhesives, and polymer components can be altered by radiation and by repeated temperature differences. The broad metal structure may persist more robustly, while finer coverings and organic compounds may gradually become brittle crack or erode under long exposure. The radioisotope thermoelectric generators form another key part of the spacecraft's material identity. They contain plutonium dioxide fuel in carefully engineered protective assemblies. Their purpose is to provide heat from radioactive decay and convert part of that heat into electricity. Over time, the fuel continues to decay, though the useful electrical output declines below operational needs. Even after that, the generator units remain as physical masses attached to the spacecraft. The plutonium itself changes predictably through radioactive decay, and the thermal situation evolves accordingly. But the larger point is that these units do not disappear when power ends. They become inert sources of dwindling internal change rather than active supports of the mission. Voyager 1 also carries small amounts of residual propellant and gas used for attitude control during its operating life. These materials matter while the spacecraft remains functional because they allow tiny thrusters to adjust orientation. Over long times, after the end of mission operations, any remaining usable quantities become less relevant. What matters physically is that tanks, lines, valves, and thruster assemblies remain part of the craft's body. The spacecraft is therefore not simply an antenna and a box. It is a complete engineered organism of hardware with systems for communication, power structure, sensing, and control, all frozen into stillness once activity ends. One of the most remarkable facts about Voyager 1's matter is that it is made from elements formed in ancient stars and assembled on Earth into a form that no natural process would likely produce. Aluminium refined and shaped into a radio dish, copper drawn into wire silicon processed into electronics, isotopes purified for long-lived power, gold applied as a protective layer to a record. All of these are arrangements of matter that carry unmistakable signs of technological origin. Even if all function is lost, the object remains recognizably artificial. In that sense, its material future is not only about survival, it is also about legibility. It continues to exist as a detectable artifact in principle, though the chance of anyone or anything finding it remains extraordinarily small. The spacecraft's mass, a little more than 700 kilograms at launch, gives it persistence. It is large enough to endure minor impacts without disappearing, yet small enough to remain only a tiny object against interstellar distances. Its surface area exposes it to radiation and occasional dust grain collisions. Its structure distributes forces unevenly. Some parts are more shielded than others. The dish may collect tiny impacts across a broad area, while edges and booms may prove more vulnerable to gradual damage. But the object as a whole is not fragile in the way a glass ornament is fragile. It is a durable machine converted by time into a durable relic, so this region of the story turns inward from path to body. Voyager 1 is a dish, a frame, a set of booms, generators, tanks, boards, films, wires, and plated surfaces. It is metal and ceramic and polymer and isotope. It is the frozen remains of functions that once spoke across the solar system. When 1 million years are considered, these materials matter because they determine not where the spacecraft goes, but what condition may remain when it gets there. Before the slower processes of deep space weathering are considered, the craft must first be seen clearly as what it already is, a human-made object of specific matter, carrying its design into the dark long after its activity has ended. Once Voyager 1 becomes silent, it does not become unchanged. Deep space is gentle compared with the Earth in some ways because there is no air, no rain, no flowing water, and no living chemistry to rapidly break materials down. Yet it is not a place of perfect preservation. It has its own slow weather. This weather does not resemble wind over rock or waves against a shore. It works through radiation temperature differences and occasional impacts from small particles moving at high speed. Over 1 million years, these influences do not erase Voyager 1 completely, but they can alter its surfaces, weaken some materials, and gradually change the condition of the spacecraft as a physical artifact. Radiation is one of the most persistent agents of change. Voyager 1 travels through an environment filled with energetic particles from the Sun, from the local interstellar medium, and from more distant galactic sources. Some of these particles are cosmic rays, atomic nuclei, and other particles accelerated to very high energies by violent events such as supernova shocks. When such particles strike spacecraft materials, they can break chemical bonds, displace atoms in solids, and cause cumulative damage to electronic and organic materials. During the active mission, radiation matters because it can disturb instruments and electronics. Over the much longer inactive future, it matters because it slowly alters the matter of the spacecraft itself. Not all materials respond in the same way. Metals often tolerate radiation comparatively well in terms of retaining their broad structure, though their surfaces can be modified and their crystal lattices can accumulate defects. Polymers, paints, cable coverings, and adhesive materials are usually more vulnerable. Radiation can make some of them brittle, darkened, cracked, or less cohesive. A thin film that serves well for decades may not remain unchanged over hundreds of thousands of years. A coating may become fragile. A flexible material may stiffen and fracture. These changes do not happen all at once, and they do not necessarily cause parts to break away quickly in the near term. But over 1 million years, they represent one of the clearest reasons to expect the spacecraft's finer outer materials to age more strongly than its basic metal frame. Temperature also contributes, though, in a quiet and indirect way. In deep space, temperature is governed less by contact with surrounding matter and more by radiation from nearby sources, and by the object's own ability to absorb and emit energy. Near the Sun, spacecraft can experience more pronounced cycles of heating and cooling, depending on orientation and distance. Farther out, those cycles become gentler, in some respects, because solar input is much weaker. Even so, parts of Voyager 1 may still undergo long-term thermal stresses, as different materials expand and contract by different amounts across changing conditions. Metals, ceramics, and polymers do not respond to heat identically. Over long spans, repeated stress at joints and interfaces can encourage cracking, loosening, or distortion, especially in already aged materials. Micrometeoroids and dust grains provide another source of weathering. Interstellar space is extremely sparse, so impacts are rare compared with anything in an atmosphere or dense orbital debris field. Yet rare does not mean non-existent. A tiny grain striking at tens of kilometers per second carries enough energy to pit a surface chip, a coating, or scar a thin layer. Most such impacts are expected to be very small. Over 1 million years, however, the total number of minor collisions may become significant for exposed surfaces. The dish booms and outer housings may gradually accumulate microscopic scars. Thin films and fragile coverings may suffer more than thicker metal structures. The effect is not likely to pulverize the spacecraft, but it can slowly roughen and erode its exposed exterior. Vacuum itself is not an agent of erosion in the ordinary sense, but it changes how materials behave. Some substances slowly release trapped gases or volatile compounds in a process known as outgassing. This is most important early in a mission when fresh materials first enter vacuum, but long-term low-level changes can continue in some components. Lubricants, sealants, and organic residues may alter over time. Without atmosphere, there is also no protective buffer against radiation and particle strikes. Every exposed surface meets space directly. This direct exposure is one reason why the thin and carefully engineered outer layers of a spacecraft can age differently from the more sheltered structure beneath them. The geometry of Voyager 1 matters here as well. The broad antenna dish presents a large area to the surrounding environment. Its surface may collect more dust impacts simply because it offers more target area. Edges and projecting booms may be especially vulnerable because they are exposed and mechanically slender. Shielded interior components enclosed behind metal housings or deeper within the central body may remain in better physical condition than external cables, blankets, or coatings. So the future spacecraft is unlikely to age uniformly. Some parts may remain recognizably intact for immense spans, while others may become fragmented, brittle, or detached. Even so, 1 million years is not necessarily enough to reduce Voyager 1 to formless debris. Space weathering in the local interstellar environment is slow. There is no oxygen to rust ordinary metals rapidly. There is no liquid water to infiltrate cracks and widen them through cycles of freezing and thawing. There is no thick medium to abrade the structure continuously. Much of the spacecraft may therefore persist in broadly recognizable form, especially the larger metallic elements. Uncertainty remains because no human artifact of this kind has yet been observed over anything like such a timescale. The expectation of long persistence is grounded in physics and materials science, but the exact appearance of the spacecraft after 1 million years cannot be known in detail. This uncertainty must be stated carefully. Observations and laboratory studies indicate that radiation impacts and thermal stress gradually damage exposed materials in space. They also indicate that robust metallic structures can survive long periods without catastrophic decay. What remains uncertain is how all these effects combine over a million-year interstellar interval for this exact spacecraft, with its exact mixture of materials, joints, coatings, and orientations. Some surface layers may disappear or peel away. Some exposed appendages may weaken. Some hidden assemblies may remain almost untouched. The broad direction is clear, but the fine outcome is not. So the slow weather of deep space is real, though it acts with patience rather than force. Radiation breaks bonds and alters surfaces. Temperature differences strain joints and layers. Dust grains leave small wounds that accumulate over vast time. Vacuum removes the comforting protections of atmosphere while preserving the object from many earthly forms of decay. Voyager 1 therefore continues not as a frozen perfect machine, but as a gradually aging artifact. It remains in motion while its materials slowly record the interstellar environment upon them, one particle strike, one broken bond, one tiny scar at a time. Attached to Voyager 1 is one of its most deliberate and symbolic objects, the Golden Record. This record is not the largest part of the spacecraft, and it does not determine the craft's motion power or structure. Yet in the long future, it becomes one of the most meaningful parts to consider, because it is designed not only to exist, but to carry a message. The record is a 12-inch phonograph disc made of copper and plated with gold. It is protected by an aluminium cover and accompanied by instructions encoded in symbolic form, intended to show how the record might be played and how its contents might be interpreted. In the quiet future, after the instruments fail and the transmitters fall silent, this record remains as Voyager 1's clearest intentional offering to any finder, however unlikely such a finding may be. The record's survival depends first on its materials. Copper is durable, workable, and stable in many conditions, while gold is highly resistant to chemical change. On Earth, gold is prized partly because it does not tarnish easily in air or moisture. In interstellar space, there is no oxygen-rich atmosphere and no liquid water to corrode it in familiar ways. This gives the gold-plated surface a favourable environment for long persistence. The record's cover, made to shield it physically and symbolically, adds another layer of protection. Together, these choices reflect the mission designer's awareness that the object might outlast the operating life of the spacecraft by an enormous margin, yet long persistence does not mean perfect preservation. The Golden Record travels through the same interstellar environment as the rest of Voyager 1. Radiation passes through and around it. Energetic particles can alter surfaces at microscopic scales. Occasional dust grains may strike exposed parts of the cover or nearby structures. Temperature conditions remain governed by radiation balance, not by air. Over 1 million years, these influences may gradually roughen, pit, or otherwise age the outer surfaces. The gold layer, though chemically resilient, is not immune to physical wear from particle impacts. The aluminium cover may accumulate scars. Fine markings and exposed etched instructions may become less clear in detail, even while the object as a whole remains intact. The record is also protected by its position and by the geometry of the spacecraft. It is not simply hanging alone in open space. It is mounted onto the spacecraft in a way that makes it part of a larger assembly. This matters because the spacecraft itself acts as a kind of partial shield for some directions and a target for impacts before those impacts could reach the record. If outer blankets, protrusions, or adjacent surfaces age first, they may absorb some of the environmental effects that would otherwise reach more protected parts. At the same time, the long-term structural integrity of the mounting matters. If joints weaken or coverings fragment, the local environment around the record may change. The future condition of the record therefore depends not only on the resilience of gold and copper, but also on the endurance of the surrounding hardware. Its informational survival is a more subtle question than its material survival. A record can remain present as matter, while becoming harder to interpret as a message. The grooves that encode sound and images are physical patterns cut into the disk. In principle, as long as those grooves remain sufficiently preserved, the information remains stored. But information is more fragile than bulk structure. Tiny abrasion, surface deformation, or accumulated pitting could make portions harder to recover precisely. The symbolic instructions on the cover also depend on recognizability. If markings are worn scarred or partly obscured, interpretation becomes more difficult. This does not mean the message is likely to vanish quickly. It means that the threshold for preserving matter is lower than the threshold for preserving fully recoverable meaning. The record also carries another kind of survival that is not purely physical. It survives as intention. The message it contains, music, greetings, images, and scientific references, is a statement made by a civilization at a particular moment in its history. That statement remains even if no one ever receives it. In 1 million years, the record may still exist, not because it has been heard, but because it has persisted as an act embedded in metal. This is different from communication in the usual sense where a sender expects a receiver. The golden record is more patient than that. It is communication prepared for a possibility so remote that the object must first survive extraordinary time before reception can even become thinkable. The chance of interception remains extremely small. Interstellar space is vast and Voyager 1 is tiny. Even over 1 million years, the spacecraft is unlikely to pass close to any planetary system, let alone one inhabited by beings able to recognize and decode an artificial artifact. This means the most probable future of the golden record is not discovery, but continued carriage through the galaxy. It remains attached to a silent spacecraft moving through sparse interstellar space, unseen and untouched by any observer. This probability does not make the record less important. It clarifies its role. The record is not a practical delivery system. It is a durable declaration placed into motion. 1 million years is long enough for that declaration to become deeply separated from the civilization that made it. Languages may change beyond recognition. Institutions may vanish. Even the memory of the mission could disappear if historical continuity were broken. Yet the record would still exist as an artifact of intention, carrying encoded traces of earthly life from the late 20th century. In this sense, it becomes a time capsule not only for hypothetical others, but also for the future of humanity itself should anyone ever recover knowledge of it. Its meaning expands as its creators recede into history. What remains uncertain is the exact quality of preservation after such a long interval. Physics suggests that the record and cover can survive broadly intact in the interstellar environment far better than they would in many terrestrial settings. Radiation and dust impacts suggest that fine details may gradually degrade. Materials science supports long persistence, but no direct observation exists for a human-made phonograph record carried through interstellar space for 1 million years. So the most honest conclusion is measured. The golden record is likely to endure as an object. It may well endure as a readable object to a significant degree, but the exact fidelity of its stored information after that time cannot be known with certainty. So the golden record enters the million-year future as Voyager 1's most deliberate inner cargo. It is small, protected, materially resilient and rich with intended meaning. Gold, copper, aluminium etched symbols and cut grooves all travel together through the dark. The spacecraft around them may age and scar. The message may remain unread. But the record persists as a compact and carefully sheltered fragment of Earth, carried onward not by hope of arrival, but by the endurance of matter and the patience of time. After 1 million years, Voyager 1 is most likely still moving through interstellar space as a silent and weathered artifact far from the Sun, far from Earth, and still nowhere near the edge of the Milky Way. The best simple estimate places it at roughly 17 light-years from the Sun, assuming its present outward speed relative to the Sun remains close to its current value, and no unusually close gravitational encounter significantly changes the path. 17 light-years is an immense distance in human terms. It is enough to carry the spacecraft well beyond the present nearest stellar neighborhood of the Sun. Yet it remains a tiny displacement within the galaxy as a whole. The Milky Way spans about 100,000 light-years. Against that scale, Voyager 1 after 1 million years is still only in the local district of one spiral disk, still part of the same broad galactic environment in which it began. At that distance, the Sun no longer dominates the scene in the way it once did. It remains a relatively nearby star in astronomical terms, but not the overwhelming center of the spacecraft's surroundings. If Voyager 1 could somehow register the sky, as a human observer does the Sun would appear as one bright star, among others altered by distance and by the changing geometry of the stellar neighborhood. Earth would be beyond all ordinary visibility, inseparable from the Sun at such range. The planets would long since have disappeared into insignificance as individual worlds. The solar system, which once filled the entire meaning of the mission, would then be reduced to a distant stellar origin, a place named by memory rather than by immediate physical presence. The spacecraft itself would almost certainly no longer be active. Its instruments would be silent. Its transmitter would have ceased long before. Its power source would still undergo radioactive decay in the physical sense, but not in any way useful for mission operations. No human civilization could expect ongoing contact across that span through the original mission framework. What remains is not a functioning probe in the modern sense, but a body in motion. The dish boom's generator housing, structural frame record cover, and enclosed components continue onward because nothing substantial has stopped them. The essential fact of the million-year future is therefore not communication but persistence. Its condition is likely to be altered but still broadly recognizable. The larger metallic structures may endure well. Exposed polymers, coatings, cable coverings, and thin films may be degraded, embrittled, cracked, or partly lost. Surfaces may be pitted by long accumulation of tiny particle impacts. Radiation may have damaged finer materials and altered exposed outer layers. Some appendages could be weakened. Some coverings may no longer remain intact. Yet no known process in the local interstellar environment is expected to grind the spacecraft rapidly into dust over 1 million years. The most probable picture is not one of perfect preservation and not one of total destruction. It is one of partial survival, a weathered human-made object scarred by deep time but still physically present. The golden record is likely still attached unless structural failure in its mounting or severe local damage has changed that condition. Its cover may bear marks of long exposure. Fine details may be somewhat worn at microscopic scale. Even so, the record probably remains one of the more durable symbolic features of the craft. It continues to exist as an encoded statement from Earth, whether or not it is ever discovered. By 1 million years, however, its practical meaning depends almost entirely on hypothetical recovery. The chance of that remains extremely small. Voyager 1 is tiny space is vast, and no evidence suggests that the spacecraft is likely to pass near an inhabited world or a technological civilization on that timescale. Its message therefore persists mostly as stored possibility. The surrounding environment at that time is still likely to be interstellar, though the precise local conditions may differ from those near the spacecraft today. The Sun and its heliosphere move through the local galactic medium. Nearby stars shift their positions. Voyager 1 itself moves through a changing three-dimensional stellar pattern. Over 1 million years, the spacecraft may pass nearer to some stars and farther from others, but no dramatic encounter is presently expected. It is most likely still travelling through the sparse medium between stars embedded in gas magnetic field and radiation too thin to resemble anything familiar on Earth. The spacecraft does not reach some final resting region. It continues within a moving and structured galactic sea. This future also reveals the true scale of the original act that set Voyager 1 in motion. A mission planned within a human lifetime produces a consequence lasting far beyond the mission's active phase. The launch, planetary flybys and engineering decisions of a few years create a trajectory that remains meaningful after 1 million years. That meaning is not practical in the everyday sense. The spacecraft no longer gathers data for Earth. It no longer responds to commands. Yet it remains a durable expression of a civilization capable of building an object giving it escape speed from its star, and accepting that its largest achievement may be measured not in immediate return but in continued existence. There is uncertainty in the finer details, and that uncertainty should remain clear. The precise future position relative to specific stars depends on the exact motions of those stars and on the cumulative effect of gravitational influences over long intervals. The exact state of the spacecraft's materials after 1 million years cannot be known from direct observation. The exact preservation quality of the golden record is uncertain. But the broader conclusion is firm. Observations and physics together indicate that Voyager 1 will most likely still exist, still travel, and still lie within the interstellar region of the local Milky Way after 1 million years. So the innermost conclusion is quiet. Voyager 1 does not race toward a final destination. It does not reach another galaxy. It does not likely meet another civilization. It simply goes on. Around it lies the sparse matter between stars. Within it remain the weathered materials of a 20th century spacecraft. Behind it, by roughly 17 light-years, lies the Sun as the distant source of its motion. Ahead of it, there is no chosen harbour, only more galaxy. After 1 million years, Voyager 1 is best understood as a silent object still carrying the direction it was given, still bearing its record and still moving through the dark with no end yet reached. The long future of Voyager 1 becomes calm when viewed without urgency. A machine once surrounded by controllers, calculations, radio dishes, and public attention now enters a span in which none of those immediate human activities remain beside it. The spacecraft keeps only what physics allows it to keep. It keeps motion. It keeps mass. It keeps the faintly altered surfaces that deep space slowly writes upon. It keeps the record fastened to its frame. It keeps the direction given by a brief era of launch windows, planetary alignment, and careful engineering. In that sense, its million-year future is not dramatic. It is patient. The galaxy around it does not notice the passage of one small artifact. Stars continue their slow orbits. Interstellar gas remains thin and ancient. Magnetic fields continue through the medium. Cosmic rays pass through the dark. The Sun itself goes on around the Milky Way, carrying the planets and their histories with it, while Voyager 1 draws farther away but still shares that larger turning. Nothing in this scene suggests completion. The spacecraft has not arrived. It has only continued. What makes the journey meaningful is not that it reaches an end, but that it preserves a trace. Matter from Earth, shaped by human intention, crosses the space between stars. Its instruments fall silent, its power declines, its surfaces age. Yet the object remains, and with it remains evidence that a technological species once looked outward and accepted distances too large for its own lifetime. Voyager 1 does not solve the scale of the galaxy. It submits to that scale and still moves through it, so the million-year picture settles into stillness. A weathered craft drifts on. The sun becomes a distant star behind it. The Milky Way remains vast ahead of it. Nothing calls it back. Nothing receives it. It continues because it was set free to continue, and in that quiet persistence there is a final kind of rest.